Next problem. Uh, an insulated, it's a problem in heat equation. An insulated rod of length L has its ends at A and B maintained at 0 degrees Celsius, 100 degrees Celsius respectively, until steady state condition prevail. The temperature of ends are changed to 20 degrees Celsius and 80 degrees Celsius respectively. Find the temperature distribution of the rod. So here it is given that this rod of length, so we have a rod and rod of length L, and at the present, at the starting point of time, it has a degree. Both endpoints as degree 0 degrees Celsius and 100 degrees Celsius, and the and we know that we are providing heat, heat. So after that, we allows heat to flow through the rod. Okay. Now, and for some condition, and there is a steady state condition, that means here each endpoint has a 100 degrees Celsius and 0 degrees Celsius and 100 degrees Celsius, and it allows to flow through the circle. Now, until steady state, that means the temperature doesn't depends upon time for some point of time. That is, there is a steady state condition. That is, UT doesn't depends upon time, and we have given the endpoint temperature, starting temperature, but we doesn't know what is the initial temperature on the road. So we want to find out what is the initial temperature on the road. That means starting time, what is the temperature on the road. But it is given that the rod has a steady state condition. That means there is no the heat or temperature doesn't depends upon time for at some particular point of time. So we know that the heat equation is tau u by dou t is equal to alpha square tau square u by dou x square, alpha or c. Uh, then 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 in the steady state condition, we know that u depends only on x, not on t. So there is no change with respect to t. Therefore, if t is constant, therefore dou u by dou t is equal to 0. Thus our equation becomes tau square u by tau x square equal to 0. So our heat equation becomes tau square u by dou x square is equal to 0. So u is here, u is only a function of x. So that is d square u by dx square. Now if we integrate on both sides, you will get to du by dx is equal to a. Now again we integrate, we will get u equal to a plus ax plus b. Now we have initial condition, initial temperature is given, u of at the first endpoint u of 0 t is equal to 0 and u of lt is equal to 100. Now we apply here to find a and b. Now if when x equal to 0, we have x equal to 0, we have u equal to 0. That implies u equal to 0, then 0 is equal to a into 0 plus b. Implies b equal to 0. Similarly, therefore u becomes ax. Now again we apply the second boundary, the second condition, u equal to 100 degrees Celsius when uh, when a equal to L, when x equal to L. Therefore you will get a equal to 100 by L. So by solving that, you will get A equal to 100 by N. Therefore, U of x0, that is initial temperature on the rod is 100x by L, 100x by L, that is U of x0. So we have a steady state temperature is there, and we find out the temperature at the initial point of time. So U of x0. Now, for the subsequent unsteady flow, that means after a particular time, the bond temperature increases to 20 and one endpoint by 20 and other endpoint to 80. So then the boundary condition becomes u of 0 t is equal to 20 and u of lt is equal to 80. And we know that its endpoints, these are not equal to 0, right? So from the above problem, we have find solution when it is equal to 0. So what we will do is, so we have the rod and its endpoint end temperature here 20 degrees Celsius, and this is 80 degrees Celsius, and here at both ends it is constant. Temperature is always 20 degrees Celsius, and here always 80 degrees Celsius. So in this case, we split the solution. So what we will do is, we will split the solution u of xt is equal to into 2. So u of xt is equal to us of x plus ut of u1 of or u1 of xt or ut of xt. That means uh, I am calling it u1 of xt. So that means this is the rod, and here on one endpoint it's 20 degree constant there, and the other endpoint 80 degree Celsius. This is throughout for any t. So on the endpoints the temperature doesn't change, so it will be constant, and here this is temperature time changes with the time. So what we will do is, we will split into us of x into plus u, where u of s of x is solution of 1 involving x only. That means this endpoint, both endpoint temperature distribution we take 2s of x, and satisfying the boundary conditions. What are the boundary conditions? So it satisfies the boundary condition u0 of t is equal to 20 and ul of t is equal to 80. So these are fixed decreases. So u1 of t is transient part of the solution, which decreases with the increase of time. And also us of x depends only on x, because its endpoint in the area will be always constant. So what we will do is, uh, so we want to find out what is us of x. So for that, so our equation is dou u by dou t is equal to alpha square dou square u by dou x square, and we know that at the end points it will be is equal to 0, because it is fixed at 20 degree and 80 degrees Celsius. So they are constant. So what you will get is d square u s by dx square is equal to 0, and if you integrate both twice, you will get us equal to k1x plus k2x. Now we know that the endpoint us of 0 is 20, one endpoint, and the other endpoint is 80. Now if we apply these conditions, these two conditions here, you will get 20 is equal to, first 20 is equal to k1 into 0 plus k2. 20 is equal to, that is first condition I am applying, 20 is equal to k1 into 0 plus k2, which implies k2 is equal to 20. and 80 is equal to next. So 20. So we here we get u of us of x is equal to k1x plus 20. Now we apply the second condition. Us of L equal to 80. Then if we apply that, you will get k1 is equal to 60 by L. 60 by L. So 60 by L. Now what you will get the condition us of x, we get us of x equal to 20 plus 60 by Lx. So we get one part. Now our solution is always equal to ux of t is equal to us of x plus ut of xt. Now we want to find out this ut, and I am calling this u1 of xt is equal to, you know that u ux of t minus us of x. Now already we know that what is the end condition, boundary points u0 t is equal to u1 0 t is equal to u of 0 us of 0 or u of 0 t minus us of 0 is equal to u of 0 t. We have given 20, that is changed to 20 degrees Celsius, and us of 0, we from here you will get 20. So 20 minus 20 is equal to 0. Similarly ul of similarly ul of t is equal to us of L plus ut of Lt. u1 of, therefore u1 of Lt is equal to Lt us. So the one, this end point is 80 and minus us of L is 80. 20 plus 60 by L into L. So what you will get it. And also we have u of x0. From the first condition, we have 100 x by L. That is, we find first we find out. This we already found. Now what is u1 of initial condition? u1 of x0 is equal to u of x0 minus us of x, which is equal to 100 Lx minus 20 plus 60 by Lx. So this is equal to, you will get 40 by Lx minus 20. Now we got what is u1 of 0 t is equal to 0, u1 of Lt is equal to 0, and I got u1 of x0 is equal to 40 Lx plus minus 20. So we got all condition, and now we will find what is u1 of xt. If we got u1 of xt, we will get the solution. So u1 of xt is given. Now since the boundaries are now 0, and we know that solution in the form, solution of a heat equation is of the form, we know that u1 of xt is equal to cos px, c1 cos px plus c2 sin px into e raised to minus c square p square t, which implies therefore we will apply the condition u1 of first condition. What is u1 of 0 t is equal to 0. Then we will get u1 of xt is x0. If we put 0, this value is 0. So this is equal to 0 into, I'm substituting here 0. So C1 is equal to 0 into C3 is e raised to minus c square p square t. Okay, so we will get this is true only if which implies C1 is equal to 0. Otherwise, this complete solution becomes 0. Now, u1 of t is equal to from and we get therefore u1 of xt we can change into C1 is 0. C2 here there is C3. C3 is there. C2 sin px into C3 e raised to minus p square n square t. P square c square t. Now, which implies, okay, now what we will do is we will apply the second boundary condition u1 of lt is equal to 0, which implies if I put here 0 is equal to u of u1 of lt is equal to, I'm giving 0 here for t. So you will get C2 sin PL into C3. Okay, now which implies either C2 is equal to 0 or C2 into C3 is equal to 0 or sin PL is equal to 0. But C2 cannot be equal to 0. If C2 is equal to 0, then this will completely become 0, which is a contradiction. So C2 cannot be equal to 0. The only problem is sin PL must be equal to 0. This quantity must be equal to 0. If this is 0, then completely become 0 solution. So sin PL is 0 implies PL must be n pi, P must be n pi by n. So our solution now changes into this form. ut of u1 of xt is equal to c2. And there is one more constant is c3 c2 sin n pi by l e into e raised to c square n square pi square t by l square. Now what is we will take Cn is equal to Bn is equal to C2 C3 for a very arbitrary value, and we will take the general solution is of the form u of xt is equal to sigma n equal to 1 to infinity Bn sin n pi x by l e raised to minus c square n square pi square t divided by l square. Now we want to find out Bn. So that is our aim Bn. And we have an initial condition u u1 of 0 x0 u1 of x0 is equal to, so what is that initial condition? 40 by L minus Lx minus 20. Now we will apply this, and also u1 of x t is equal to, we have sigma n equal to 1 to infinity Pn sin n pi x by L into e raised to minus n square pi square t divided by L square. So u1 of 0 t is equal to, sorry, x0 is equal to sigma n equal to 1 to infinity Bn sin n pi x by L. And what is u1? u1 of x0, that is 40 L x minus 20 is equal to sigma n equal to 1 to infinity Bn sin n pi x by L, which implies Bn is equal to 2 by L integral 0 to L, that is by Fourier series, by Fourier formula because this is a half range Fourier series. So here Bn will be by Fourier formula 2 by L integral 0 to L 40 x by L minus 20 into sin n pi x by L. Now we will, if we integrate this, you will get so I'm not doing the integration. If you integrate this by for normal integration, you will get the answer is minus 40 by L by n pi minus 1 power n plus 1 minus 1 power n plus 1. That is B. Or you can write if n is odd, this becomes 0. This becomes 0 and n is even, this becomes 2. So this is the answer. Therefore, ut of xt is equal to sigma n equal to, I am writing this only, n equal to 1 to infinity minus 40 by n pi minus 1 power n plus 1 into sin n pi x by L n pi x by L into e raised to minus n square c square pi square by L square t, which implies, therefore our final solution is, this is u1 of t, so final solution is uh, what is final solution, us of x plus u1 of xt. This is our final solution. So from where we will get the final solution, this is the final solution also. So we will apply that. So our final solution will get ux of t is equal to us of x is, us of x we found that us of x is us of x u, us of x is 20 plus this is us of x, right? 20 plus 60 by lx, 20 plus 60 by lx, 20 plus 60 by lx, 20 plus 60 by L into x plus, now u1 of x is this quantity. So n is equal to 1 to infinity or n equal to e1. If n is e1, then this is minus 80 by n pi sin n pi x by L into e raised to minus c square n square pi square t by L. So this is the final answer. So the step is, first you find out the initial temperature on the body by using endpoint temperature. Then what you will do is u of xt is temperature on the transient side and the endpoints. So this is u1 of xt. Then you find out what is u1 of xt, and then finally you put this, substitute the answer here. So you will get the answer.